So you see Gibbs free energy change. Okay, you know that you need to memorize the formula. Okay, how do we derive the formula? It's not important anymore. Yeah, because of the change of the syllabus. Okay, so this one, make sure you know how the formula is being applied. Yeah, Gibbs free energy is going to be delta H. Okay, minus delta T delta S. Okay, so you must remember this. Okay, temperature must be always in Kelvin. Okay, please remember that. Okay, most of the time, temperature in Kelvin, it starts from absolute zero all the way. So it's going to be always going to be positive. That is one thing that you can remember as well. Okay, now Gibbs free energy. Okay, if you want to calculate, I told you that you need to be very careful when it comes to calculation, because the signs are different. The units are different. Okay, which is going to be enthalpy change of reaction is going to be kilojoule, but your entropy is going to be in joule. Okay, so you need to change them into the same units. Okay, so change them into joule. Okay, and then you calculate. Okay, calculate the enthalpy change of system, which is going to be product minus reactant. Okay, you calculate accordingly, and you will get this value. Okay, and then we can calculate the Gibbs free energy by using the formula. Okay, if they did here, they give you the temperature, but sometimes they don't give you the temperature. The moment you see this symbol over there, this shows a standard condition. Standard condition is 25 degrees Celsius. Do not use 25 degrees over here. Okay, the T must be in Kelvin. So you use 298. Always remember this. Okay, because students always make the same mistake. So when you do that, finally you will get a value. It's okay, it's fine to leave it in joule, it's fine also to convert into kilojoule, up to you. Okay, but what is important over here is going to be the unit. Okay, the signs. Okay, the sign, not the unit, the signs. The sign, if it is going to be positive, what does it tell me? Okay, Gibbs free energy must be always negative in order to be spontaneous. Okay, in order to say that reaction is feasible, it must be negative. So in this case, if your value of Gibbs free energy is positive, it means that the reaction is non-spontaneous at what temperature? You must tell they are non-spontaneous at 298. So this is another important thing. You must mention the temperature. Yeah. If you go for examples, I will not show you all these examples. Okay, you can calculate yourself. Yeah, same way that I show you just now. Okay, but if you see the final answer is going to be negative Gibbs free energy, therefore the reaction is spontaneous at what temperature you need to mention. Okay, if let's say the second reaction is going to be, you calculate and you get negative value. Okay, it means that the reaction is spontaneous. At what temperature you must mention. Yeah, all this you must mention. Okay, so further reactions and so on, you try yourself. Okay, I think we went through this in the class, but of course I didn't go through one by one. Okay, but I want you to calculate yourself. All the answers are there. Okay, try yourself. Yeah, try yourself. All these are taken from your textbook. Okay, and I told you I prefer the old textbook. Okay, compared to the new textbook. Okay, so I take and I will adjust all the content. Okay, based on the syllabus. Okay, so you won't have anything missing and you won't have anything additional. Everything is there. Okay, maybe it's missing in your textbook, but everything is there in my PowerPoint slide. Yeah. Now, prediction of feasibility of the reaction. This one, I think it's good to recall everything back. Yeah. Yeah. So there are 4 conditions. Okay. So you see enthalpy change that is going to be negative, entropy that is positive. Okay, do remember if you have different sign, okay, what you need to remember, the first thing in your head, it must be, different sign must be easy. I want you to remember this. Different sign must be easy. Yeah, you see here, okay, different signs, okay, I want you to remember it's easy. Okay, that's first thing. And here, okay, if you see enthalpy is negative, you see this value is negative. Okay, this value is negative. And entropy is positive. Do remember your temperature is positive. Okay, if this one is positive, do remember negative and positive is negative. Yeah. So let's say, for example, negative 50. Okay. And then whatever value, negative and positive, you are going to get a negative value. Whatever value, you will get negative 55. Means in the end, you are going to get a negative value. Okay, at any temperature. It means that that's the reason why I put it as easy. Why? Because at any temperature, okay, this is going to be negative. Therefore, it's spontaneous. Okay, spontaneous. If your enthalpy is negative, entropy is positive. Yeah. If you have this kind of situation, I'll use the same example. Enthalpy is positive. Okay. And entropy is negative. If this is negative, negative, negative is positive. Okay, so if it is like similar 50 plus 5, for example, whatever value, yeah, so 50 plus 5 is always going to be plus 55. Okay, whatever temperature, it's always going to give you a positive sign. It means that this is going to be always going to be non-spontaneous at any temperature. Okay, non-spontaneous at any temperature. Okay. What is the easiest way to remember? Okay, this one, okay, you see here, enthalpy negative, delta H is negative, which is going to be exothermic. Entropy is positive. It means they are in a havoc manner, okay, in a very disordered manner, okay, disorder. And then temperature is going to be very hot. They like to move around. Okay, of course, the reaction will happen spontaneous. You can predict. Okay, now if you have, okay, this delta H is positive, okay, it's going to absorb energy. Keep on absorbing, it needs to take the energy. And then the entropy, after absorbing also, the entropy change is going to be negative. It means they are absorbing and then still they are ordered. I want, okay, feasible means I want them to become disordered. Okay, I want them to become disordered. So in this case, I can predict that this is going to be non-spontaneous. You predict. Okay, you can predict. So if you have, okay, a situation, let's say, for example, both of them are same signs. Okay, same signs. Okay, so negative, negative, okay, positive and positive. This one is slightly, maybe you remember hard a bit. Okay, you need to, it's a bit complicated. Okay, you can remember that way. Negative and negative, positive, positive is a bit complicated. Why? Okay, I'll show you why. Okay, if this one is going to be negative, delta H is negative. If your entropy is negative, okay, if your entropy is negative, so it means that negative, negative is plus, right? Okay, negative and negative is plus. If you have negative 50, if I add, okay, if I add 5, I will get maybe negative 45. Okay, but negative 50, if I add 60, what will happen? Okay, why I get a bigger value? Because of the temperature. If the temperature is higher, maybe I get 60. Okay, what will happen? I am going to get positive 10. You see, it can be either, sometimes it can be spontaneous, sometimes it is going to be non-spontaneous. Okay, so this one is hard to predict. Okay, it's hard to predict. And I will teach you also, I think I taught you also how to predict them. Okay, so the same situation will happen over here. If this one is positive, my entropy is positive, positive and negative, negative. Okay, so if this one is 50, so minus 5, maybe I'll get 45. Okay, but 50 minus 60, for example, I'll get minus 10. So difficult to determine. Why we have different value? Because of the temperature. The temperature can change. Yeah, whether it's going to be high temperature or low temperature. Yeah, earlier just now, no problem. Okay, at any temperature. Okay, you can say it's spontaneous or non-spontaneous, but this one is harder to say. Now, how do we do that? Yeah, so but before I go into that, if I summarize everything, okay, if you have different sign, first thing I told you to remember is easy. Different sign, easy. How? Okay, delta H and your delta S, delta H, delta S, okay, if it is going to be different, let's say plus, minus, negative, plus, for example, which one is going to be spontaneous, left or right, Dylan? Which one is spontaneous, left or right?
Right.
Okay, entropy is getting disordered. Okay, disordered, very hot. Okay, very hot. So they like to move. Okay, they like to hit each other. Of course, this is going to be spontaneous. So this one is going to be the other way around, non-spontaneous. Very easy to identify. Easy. That's why it's easy. Okay, let's go for something that is going to be a bit hard. Okay, same signs. Okay, so if I want to visualize this, okay, the best way to visualize this is, okay, by using this solid and then liquid method. Okay, this is very, very important, very, very easy to visualize. Ice and water as an example. Okay, I'll just use twice, ice and water. Okay, this one is going to be like this. Okay, since I'm using H2O, let's say the temperature I'm going to use 0 degrees Celsius. Okay, so ice can change into water. Okay, when ice change into water, okay, so when ice change into water, delta H must be positive. Okay, it must absorb energy, then only they can break the bond. Okay, and then your entropy change, because from ordered, it is going to become disordered. Okay, which is water. So this one is positive. Okay, if you go the other way around, water change into ice. Okay, you will see that. Okay, this one, if I separate them, you will see that your delta H, okay, water to become ice, okay, is going to be minus. Okay, something that is very able to move, and then suddenly they become very rigid. All the energy goes where? Outside to the surrounding. Okay, exothermic. And then your entropy change now is going to become from disorder, water is disorder, and then ice is going to be ordered. Okay, so your entropy change is going to be minus. Okay, not it is going to become ordered. So you can see here, what is important over here is, okay, the signs are the same. Now the next thing that I need to find out is, ice turns into water under what condition? Okay, ice will change into water under, okay, above 0 degrees, when it is above melting point. Okay, so it means it will not happen over here. It means that this reaction is spontaneous for water, yeah, okay, when the temperature is higher than 0. We can use this example for any of these example over here. I will just simplify. The reaction is going to be spontaneous if the temperature is higher. Okay. And this one, the reaction is going to be spontaneous. Okay. Water change into ice. Okay. It will be spontaneous under what condition? Yeah. So it must be at this below 0. Yeah. Then only it will change into ice. So this one is non-spontaneous. So it will be spontaneous at lower temperature. Okay. Now, if I want to simplify, let's say I want to memorize straight away, easier way to memorize. Okay. What is the easier way to memorize? If you have both of them same sign, positive, positive, you memorize, think positive. Positive, positive, think positive. Negative, negative, think negative. Okay, if you follow that way. Okay, so if I put it over here, okay, if I want to predict, okay, with different same signs, okay, I can just say that, okay, if my delta S and delta H, positive, positive, negative, negative. I told you, positive, positive, think positive. Negative, negative, think negative. When this reaction, the reaction is going to be spontaneous under high temperature. This reaction is going to be spontaneous at lower temperature. So if I represent this, okay, in form of quadrant, I went through this with you guys, okay. If you have this one is positive, negative, let's say positive and negative, okay. I know this quadrant is positive, positive quadrant, negative, positive quadrant, positive, negative quadrant, and this is going to be negative, negative quadrant. And I told you, okay, which one is easy Different is easy. Okay, different is easy. If your enthalpy is negative, okay, and your entropy is positive, then it's spontaneous at any temperature. You can come up with this. If your entropy is negative and the enthalpy is positive, then it's non-spontaneous. Quite easy to remember. Okay, and this one also very easy to remember now by this time. Positive, positive, think positive. Negative, negative, think negative. Okay, so how? This reaction is only spontaneous at low temperature. And this reaction is only going to be spontaneous. Sorry, I think I made a mistake. At higher temperature. At high temperature. This is only going to be spontaneous at low temperature. Very easy. Yeah, very easy to represent. Now, are we required to come up with this table? No. Actually, there is no point of coming up with a table. Okay. What you need to know is by this time, you should be able to predict the effect of temperature change. Okay. And that quadrant is going to help you. How? You no need to remember the quadrant. Yeah. Some of you, they prefer quadrant. Okay. So I think for me, it's very simple. Plus, minus, plus, minus. If you have something that is different, easy. Remember, easy. If, let's say, for example, my entropy change is positive, my delta H is negative, okay, it means that this is spontaneous. I need to know. Okay, so this one is going to be, let's say, this one is going to be delta H and then delta S. I know that this is going to be non-spontaneous. Okay, I need to find out that. Okay, and then, okay, let me see the chat. Hold on. Okay. Now, and then, okay, if I have something that is going to be like this, okay, negative, negative, delta S, delta H is going to be positive, positive. Same sign, okay, I told you very easy also. Negative, negative, think negative. Positive, positive, think positive. Okay, the reaction is going to be spontaneous at lower temperature. The reaction is going to be spontaneous at higher temperature. Okay, now of course, okay, you want to know how it is being applied. Yeah, okay, this one, try with your teacher. Actually, no need to even try with me. Okay, you try yourself. Yeah, the answers are given there. Okay, you try yourself. Okay, but I will go through this question with you. Okay, this one also you try yourself. Okay, I think all this when I went through with the other class, yeah, it took some time from me. Yeah, so I want to just achieve what today's lesson and additional part on the electrochemistry today. Yeah, so you see here, okay, they want you to calculate Gibbs free energy. What you need to do first, change this into, do remember this is now in kilojoule. Final answer must change into kilojoule. Okay, up to you whether you want to keep it into kilojoule, you want to change this into kilojoule, up to you. Okay, but I will try to use 11700 first, joule. Okay, and then I need to find my Gibbs free energy. First of all, I need to find what is my entropy change, which is going to be entropy of the product minus entropy of the reactant. Okay, what is my entropy of the product? Entropy of product, carbon dioxide 214 plus MgO 26.9 minus entropy of the reactant, 65.7. Okay, there is no number over there, no need to times anything. Yeah, so I calculate. Okay, I will get a value. Okay, maybe someone can help me with this. Yeah, and while you guys are doing, and you will use the formula. Gibbs free energy is going to be delta H minus temperature. This one, temperature. Okay, they didn't give. They give. Okay, sometimes they don't give. Okay, if they don't give also, if you have this symbol over there, use 298. Okay, 298 times this one. Okay, so use the formula, all the values that you have over there. Okay, minus 298. Okay, whatever value that you have here, you put it over here. you should get, okay, this one no need to debate on it. You will get the answer in joule per something. You need to divide it by 1000 so that you get this answer. Okay, please remember it's in kilojoule. Okay, so once you do that, okay, it means here, yeah, this is in joule, in joule. Okay, this value is in joule, and then you need to divide by 1000. Okay, divide by 1000 and you will get this value. Yeah, so whatever it is, you will get this value. Okay, the answer is that. Okay, it's going to be positive 64.8. What does it mean? Okay, this reaction is non-feasible at 298 or non-spontaneous at 298. Okay, please remember you need to mention about the temperature. Yeah, now the question over here will explain, okay, about, okay, why we learn about the quadrant. Okay, I'll teach you why we learn about that quadrant. You see here, okay, this delta H is going to be positive. Okay, this Gibbs free energy, okay, is positive. Okay, is positive. So I need okay, actually no need to worry about this Gibbs free energy. You need to just worry about this value, entropy. Okay, the entropy, okay, is going to be positive. Okay, this value is positive. Entropy is positive. So you see, positive and positive, same value, same sign. Okay, same sign, little bit difficult, but it's okay. Positive, positive, think positive. The reaction will be spontaneous only when the temperature is high. You see why the reaction become more feasible at high temperature. Okay, you need to explain why. Okay, in this case, they ask you to explain why the reaction is more feasible. It means your Gibbs free energy is negative. Okay, then only is feasible when, okay, higher temperature. Because, okay, you need to mention because what will happen? Delta G equals to delta H minus delta T minus this E delta S. It means that I know this value is 117. I want Gibbs free energy is negative. Okay, so what I need to have, this value, okay, this value must be greater than 117, maybe 118. Okay, I will get a negative 1 value. Okay, it means that I need to tell that at higher temperature, my T, this one, okay, is more positive. Okay, it's more positive. So this is what we want. Okay, so you see, this is more positive, Gibbs free energy is negative. This is why we learn about that quadrant. Okay, this is why, not direct application. This is more towards explaining. Okay, but if they ask you to predict without calculating, then you can predict using the quadrant. Okay, but this is one of the application of that quadrant. Yeah, this one I want you to understand. Even though it's only 1 mark, yeah. Okay, very crucial in understanding the concept. Okay, very crucial in understanding the concept. Okay, anyway, okay, the first part is done. Okay, on time. Okay, now it's 3 o'clock. Okay, so we have another 30 minutes. Okay, so we will enter lecture 9. Okay, electrolysis part 2. Okay, now for the electrolysis, okay, do remember it means that entropy, okay, is done. Gibbs free energy is done. Okay, now we are going to enter electrochemistry, yeah, which is, I told you, is going to be difficult. Okay, but do remember today's lesson is not that difficult. Yeah, so it's actually quite easy to understand. Yeah. Now, what is electrolysis? Okay, electrolysis, I think you should know about electrolysis. You use battery, yeah, you use power source, and you decompose a compound, okay, using electricity. And okay, we have to have electrolyte. Okay, the electrolyte that we use must be able to conduct electricity. It means it must be in aqueous form. It can be in molten form, okay, or it can be also concentrated. And then, okay, we need to use electrode. Okay, of course, we want it to conduct electricity, right? So electrode must be carbon, okay, or metal, anything that can conduct electricity. You don't go and use PVC over there. Okay, so it must be something that can conduct electricity. Even graphite also can. Okay, platinum also can. Don't ask me why I didn't write over there. Actually, you should know. Yeah, all these, anything that can conduct electricity can be used as electrode. The anode is